So next is this section of solids. So we have up till the last one, we have done this projections of solids, and next is the sections of solids. So primarily in this projections part remains say more or less similar to whatever we have done, with one change that we try to get some additional information about the object by assuming that
भाई चार्जर लाए नहीं हो यार तुम।
so, yeah, please switch, keep yourself muted. Ujjwal Shah. Yeah. So before this projections of solids, of course, whatever we have done is projections of points, lines, and planes. So one particular change, what we observe when we started this topic projections of solids, is that we have got some part of the object which is hidden, and then we try to show it using the dashed lines, right? So there might be some features related to the part which will be hidden. So that is one aspect which is associated with the solids. So this sections of solids primarily in this topic, what we try to do is we try to assume that there is a cutting plane which is passing through the solid. So this cutting action is referred as sectioning. Okay, so this cutting plane passes through the solid, and then that part is imagined to be cut, and then one part is assumed to have been removed from the object, and for the remaining part then we draw the uh, view. Okay, for the remaining part we draw the view. So of course then from wherever we assume the cutting plane to pass through, in that portion we'll have some additional features which will become visible to us rather than being hidden, and thus we'll have some more information about the solid available. So that is the thing, for which we need this sectioning part. Okay, now here is what generally used for the sectioning, that is shown here. So primarily two types of cutting planes we'll be using in this topic. So one possibility is that the cutting plane is perpendicular to the horizontal plane, or else it is perpendicular to the vertical plane. Okay, so this view here, let me change the pointer. Yeah, this view here is only the front view of a cone. So here cutting plane has been shown. So this is either can be referred as cutting plane or section plane. So in general, we'll always call it section plane. So whenever we have any section plane which is perpendicular to the vertical plane, then in the front view we'll obtain it as a line. So a line is shown over here. So this is representing a cutting plane or section plane. So what then is done is then we imagine that say this part is removed, okay, and then we see from the top, right, and then obtain a top view. So we'll have a cut section portion available in the top view. Likewise, if we are using say a section plane which is perpendicular to the horizontal plane, then the situation will be like this. So in the top view, it will look like a line. So we'll draw it in the top view. Then again, say this part we assume to be removed, and then we draw the front view. So the front view will have the cut section portion which will be visible. This part is removed, so the remaining part will be visible. So when we draw a view in which the section part is visible to us. So that is referred as a sectional view. Okay, so like for this case, this is the top view in which the section plane is shown. When we will draw the corresponding front view, it is not on this slide. When we draw the corresponding front view, that we will call a sectional view. Okay, now in order to distinguish between the portion which is sectioned and the portion of the object which is not sectioned, the sectioned part is shown with uh, lines drawn parallel to each other close by. These are referred as section line or hatching lines. Maybe next slide might have this. Yeah, here. So the portion through which the section plane is passing and which is visible to us, that actually will have these kind of lines within that. So these darker lines, right? Like this is a rectangle. So whenever say the part which has been cut by a section plane, okay, suppose it is looking like a rectangle, then you see the boundary of this rectangle is drawn darker and relatively lighter section lines are drawn like this. This is also termed as hatching. This process is termed as hatching. These lines actually have to be inclined to their corresponding boundary. So like this is of course a rectangle. So inclined with the boundary, these lines are drawn. And then depending on how much bigger this overall size is, we have to draw these lines so that there is some sufficient thickness of the line or sufficient density of the lines available. Here also say corresponding, with reference to the boundary, see in inclined lines. So as such, these lines look horizontal, but since the boundary actually is inclined, so these section lines are having inclination with the boundary in this diagram. Likewise, here it is elliptical. So then, of course, the boundary is curved. But all in all, some sort of section lines are to be chosen which will be inclined to the boundary so that they look completely different in comparison to their boundary. Okay. So yeah. Now here you see one simpler demonstration is available in this slide. So you see square pyramid actually is shown. So in this pictorial view it can be seen. Here is a square pyramid. Then to obtain the sectional view, what has been done is that a section plane which is perpendicular to the vertical plane has been shown over here. Okay, and for this particular case, this has been kept parallel to the horizontal plane. So a section plane which is perpendicular to vertical plane may or may not be parallel to the horizontal plane. For this case, it is parallel to the same. Now you see how the corresponding section plane is to be represented in the front view, that is shown over here in this vertical plane which is drawn in this pictorial view, and it is also then shown in the front view here also. So this is the front view for the given case, and this section plane is passing through this part. So the section plane is shown by the center line, that is which is drawn with a long dash and a short dash alternately. And the end points, actually here these ends have been made darker here and here. What I would recommend actually is that this darker part should be closer to the boundary, that is somewhere here. Okay, and then thereafter these arrow marks can be put so as to show the direction in which the object is being observed, right? And then here is what the sectional view is. So you see the section plane is passing through this part, so this upper part is assumed to be removed, and then for the remaining part we obtain the top view. So of course, when we begin drawing it, we'll have to draw the top view, whatever we draw for the usual case. Thereafter, we'll have to locate the toe. This is the section plane passing through here on the face. So we drop this point over here. We locate this two, this one. We draw this point here. That by dropping, what I mean is that we draw a projector from here. It will intersect this top view for this slant edge here and here. 3 at 3 and 4. So we'll locate these corners where the sectioning is happening, where the section plane is passing through. And like this, we'll locate all these 1, 2, 3, 4, and then this part is then to be hatched, or section lines are to be drawn in this. Okay. So here for this case, of course, you see the section plane is parallel to the horizontal plane. So this sectional view, this thing, is 1, 2, 3, 4 will give us the true shape of this section part. Then here few more situations similar to what we have seen in the previous diagram, right? So here the section plane is shown perpendicular to vertical plane and parallel to horizontal. For this case, perpendicular to vertical plane but inclined with the horizontal. And then here in case say a cylindrical object is sectioned by this plane, then we'll have this kind of top view for this case. Same top view actually will be existing for this case also, although the plane is inclined. And this surface, the surface of the section will not show a circular surface. It will be elliptical since this is inclined. But in the top view, of course, still it will remain circular. So that is what is depicted. Then similarly here we have the opposite of the same. That means section planes are perpendicular to the horizontal plane. For this case, apart from being perpendicular to the horizontal plane, it is parallel to the vertical plane. Okay. Again, passing through the cylinder, the section part is shown with the sectioning lines or hatching as shown here. Here, section plane is perpendicular to the horizontal plane and inclined with the vertical plane. Again, section part here, hatching is shown on the portion which is section. In the side, you see here we have some part which is through which the section plane is not passing. So it is intact. So there no hatching lines are there and it is shown intact. Again, a similar case where a cube is being sectioned by this, okay, the overall thing you have. These are certain say cases like if cylinder is cut by a section plane which is inclined with its axis, right? So you get an ellipse. If it will be parallel, it will be circle. Here this pyramid is cut by a plane which is as such inclined with respect to axis, then you get a trapezium as the cut surface. For the case of cone, these are the four possibilities. If it is passing through the apex, then you will have triangular face. If it is not passing, then parabola. Okay, and if it is passing through both the sides, then an elliptical surface. These you can have a look later. Now this particular diagram here shows the complete terminology when you have to draw the section views or any section of solid. So here you see pyramid has been shown, right? Then there is a section plane which is perpendicular to the vertical plane, and then it is passing through say midpoint of the axis. And usually there will be some inclination of this plane with the horizontal plane also mentioned. So say with the given information, we draw this top view and front view. Thereafter, we have to locate the section plane. And then again, we'll draw the projectors from here to locate this corner point for the section surface. Projector from here to look at this corner point, and then we draw the section. For this case, this section plane is not parallel to the horizontal plane. So here we don't get the true shape of the section. So this may be referred as the apparent section or shape of the section. In general, this will simply be this is a top view, of course. This will be referred as the sectional top view because the normal top view will have all these edges meeting at the center, geometric center, which will represent the top view of this apex. Okay. Then in order to obtain the true shape, now what we need to do is with the parallel to this available section plane, we have to choose new XY line, and then only for this surface, this much surface, we'll draw an auxiliary view as shown over here. Okay, so new x1 y1 has been chosen, and for this much part an auxiliary view has been drawn. This will give the true shape of the section. So this is how usually we'll have to proceed. One more thing let me mention here. In this diagram, you see, as I had mentioned, this section plane is shown with the long dash and short dash. Okay, this is the center line, whatever we call long dash and short dash. With that, this is represented at the ends. I mean, wherever the section plane is reaching the boundary of the object. Beyond that, you draw the darker line here also, here also. Okay, so like that we show the section plane. Then you see the portion which we assume to have been removed, that is this upper part for this case, is assumed to be removed. That is drawn with less dark lines. The remaining portion will be darker in comparison to this. Okay. So these things actually will have to follow when any particular problem is being solved and any particular sectional views are to be drawn. Now let us have a look at this problem. So a hexagonal pyramid, base 30 mm side, axis 65 mm long, is resting on its base on the horizontal plane. Two edges parallel to the vertical plane. Right. So initial, then again somebody has not muted himself. Janam. Yeah. So please mute yourself. Yeah. So with this first line is giving us one thing is how much is the dimension of the base, hexagonal base of the pyramid, and then we have this height of the axis, right? So the information for drawing the hexagonal pyramid is available. Then if for the initial condition there is additional condition given that two edges parallel to VP. So base has to be kept on the horizontal plane. Base is to be kept on the horizontal plane while keeping two edges of the base parallel to the VP. So this has to be maintained. We can draw it. And then it is cut by a section plane perpendicular to the VP, inclined 45 degrees to the HP, and intersecting the axis at a point 25 mm above the base. For this, actually, the complete solution is there, so I will bring it here. A stepwise thing I don't have. So you see, with the given information, first of all, the top view and front view of the hexagonal pyramid, this side and this side, the two sides are parallel to the vertical plane. That condition fulfilled. 5, 6, and 2, 3 parallel to the vertical plane. With this, by keeping them parallel to XY line in the top view. Then next you have to look at the section plane. So it's 45 degrees. So we'll have to draw 45 degree to the XY line. That is one thing. And then it is 25 mm above the base. So from here we'll measure 25 mm. Okay. Thereafter it is drawn. Then what next? Then we assume that the upper part is removed. Right. Thereafter, wherever it is intersecting the edges, like G dash, one edge is being intersected, O dash, F4 dash. This is a slant edge. It's intersected at G dash. So from G dash we draw a projector where onto the top view of this same edge. So here it is O dash 4 dash. Here you will have O4. Okay. From G dash you will come down to this O4. It intersects here. You will locate this G. Likewise, at this location we have two edges overlapping, O dash 3 dash and O dash 5 dash. Right. This is this line from here to here. This is representing two edges. The two edges are intersected here. E dash F dash. So to know that, again we have to draw the projector. So O5 top view is here, intersected at this location. One corner point obtained. O3 with the same projector intersecting O3 here. We look at the other point. Okay. The same has to be done for this also. So one endpoint located here, one. We have this O2 is this, it is intersected at C. O6 is this, it is intersected by the projector at D. Hereafter what's happening, it is passing through the base. This is the corner of the base. So we actually are getting inside and intersecting the base. So this corner actually is getting removed, right? Now since here the base is being intersected, so the base is hexagonal shape, right? In the top view available, we draw the projector here onto the base shape, so it intersects 1,6, edge of the base 1,6 here, and edge of the base 1,2 here at. So then we look at this A and B, right? So like this we get the overall corners of the surface which is being obtained due to this section plane passing through this. So you join these all, then this part is to be shown with the section lines. Okay. Then again this will be the sectional top view, and you can see this part, which this part is assumed to have been removed. So this is to be drawn with less darkness, right? Lighter as compared to the rest of the part. Here also this upper part we have assumed to be removed. So this is to be drawn lighter, the remaining part darker. The section plane, whatever we have seen in the previous slide, right? So please follow that for the section. Okay. Then this here only it is showing a dashed line for the section plane. So you please use whatever we discussed in the previous slide. Yeah. Now, in order to obtain the true shape, again this x1, y1, we have to choose parallel to this section plane. Okay, parallel to this x1, y1 chosen. Then you draw all these projectors from these different corners, whatever we obtained on the different edges. Once you get this, then again measuring distances away from the xy line for all these corner points in the top view, wherever these corner points are situated, that is how much away from xy line. The same distances will mark away from this x1, y1 on the relevant projectors. Locate all the corners, and this section view will be completed like this. Okay. Fine. Now let us have a case of the square prism. So again you have base 40 mm side and height 80 mm, as its base on the horizontal plane and faces equally inclined to the vertical plane. So again we have the side of the base 40 mm available, then height is 80 mm, right? And then its base is on the horizontal plane in such a fashion that its faces are equally inclined to the V. So this actually will be for the case of lateral surfaces, that right? That is the rectangular faces, whatever will be available for the square prism. Those are to be equally inclined. So that means that position in the top view is to be such that the sides of the square will also be inclined equally to the what do you call xy line. That means one of the diagonals will be perpendicular to the xy line for the base and one will be parallel. Like that we draw the top view and then we get the front view, right? So this much will be similar to whatever we have done. Beyond that you have that it is cut by a plane perpendicular to the VP and inclined at 60 degrees to the horizontal plane. Okay, and passing through a point on the axis 55 mm above the horizontal plane. So again, we can locate this section plane with the given inclination and then draw the front view, top view, and the side and the true shape of the section. Fine. So here is it. So you see, first of all, these sides have to be in the initial position kept inclined to the xy line equally. One diagonal parallel for the base, then we get this. Now, yeah, you see here, this each corner here will represent 2 points, right? And then we have, after drawing this, we have to maintain this. In this diagram as such, you have these 1 dash, 2 dash, 3 dash, 4 dash, right? And then 5, 6, 7, 8. But usually it could be like for one surface you can have numbers, for one you can have letters as we discussed. Here only for the reason that this part may be given the names with the letters so that it is distinguished from the rest of the figure. This thing has been done, giving numbers for the top and bottom faces for the naming. Okay. Now you see, so with the given information at this whatever given height 55 mm, a section plane with the 60 degrees is to be drawn. Then one corner we get here, two will get here because here we have two edges, and again two will have here because it is intersecting the top face, and this will be actually resulting into two edges from here to here. This edge at the top part and this one. So here corresponding to this location we have the part which is not sectioned, so that is why it is shown without any uh, what do you call, without any section lines, but the rest of the part is section. The true shape again has been drawn by choosing a new XY line and then drawing the auxiliary sectional side view. So again this part we are assuming to be removed and then drawing the side view also. So the distances can be taken for the side view in this fashion, or else if you want then you can measure these distances and then mark them directly away from this new XY line. Either way you can proceed. Okay, so we can discuss this one briefly and then maybe stop for now. So square pyramid, base 40 mm side, axis 65 mm I guess, has its base on the HP and all the edges of the base equally inclined to the VP. It is cut by a section plane perpendicular to VP, inclined 45 degree to HP and bisecting the axis. Again draw the sectional top view, side view and true shape of the section similar to the previous one. Only thing is there it was a pyramid and here, oh sorry, there it was a prism and here it is a pyramid. So primary difference, of course, you can see here all these edges were parallel to the axis of the solid, right? And there all these will be joining the apex in the next problem, right? Rest of it is similar. The one difference what we have is here this actually say like this middle part if you consider. Here the section plane is passing and intersecting this. Then it is actually intersecting complete thing. So one corner we are getting here and one here, because these edges, I mean, see, you have an edge over here, right? Say 2 6 and the 4 8 as per the nomenclature here. These are coincident, and these are individually giving point view. One is here, one is here. So they are intersected by the plane at this part, and then here you are obtaining this. That is, you are obtaining the what you call corner point for the where the section plane is passing. Here the situation will change, right? First of all, this part with the given information 45-degree top view drawn, then front view drawn, right? Then we have to look at the section plane. So it's passing through, it's bisecting the axis, right? It's bisecting the axis. So point you will locate, and a 45-degree line is to be drawn. Located. Now endpoints to be darker. Yeah. Now you see, now we have to locate these in the top view. So here this O dash I dash is representing a long edge. Top view is obtained here OA. So from here we draw a projector and locate the point of intersection. Obtained here. Right. Same way from here also we can obtain it here. Right. O dash C dash intersected at this location. So that is why projector drawn on OC intersection gives this intersection point. Now you see in the previous case, I specifically was mentioning, previous case we had a prism. So point corresponding to this, of course, we are located here and here, right? But for this case, that will not be possible because these are slant edges. Here also these two will be slant, but we cannot see that in this front view, right? So now for this point or this point, drawing a projector successfully gave us this location wherever it is intersecting the edge, right? Here in the front view, of course, we are able to locate here, here, and here. In the top view, what we are doing, we draw the projector corresponding to it on the corresponding top view. O dash C dash here, OC here. So here the projector intersects. And this marks as the intersection point in the top view points. So for this thing will fail because this edge OD and this OB, these will actually lie on the same projector. So if I draw a projector from here, it will be coincident with the edges. So specific intersection points like here and here we cannot obtain. So for such a case, what actually is to be done is that this OB, right, like we have this OB here, this is to be rotated and made parallel to the XY line. Okay. Then corresponding front view for this OB is to be obtained, and then this is to be projected here, and the same will give us the point. For this particular diagram, this exercise is shortened by one step, that is rotating OB and making parallel and then obtaining corresponding front view is not needed, because since OB and OA are completely identical for the square pyramid, the slant edges are all identical, and here whatever, if OB is rotated, it will simply overlap with the OA, and the new O dash B1 dash will be coinciding with O dash A dash. So we skip with rotation part, right? We skip with the rotation part, and we consider this OA and O dash A dash for our purpose. Yeah, next what I mentioned is move parallel to this XY line from this point of section which is available in the front. Move parallel to the XY line. We reach here. Then this point marks the location where the intersection is to be considered. This is to be brought onto this horizontal edge, top view of horizontal edge. Okay, here. Then from here we travel back to this one. Okay, like this we locate corresponding points of intersection for this part. Go here, come down, and then here. So same process for OB also, for OD also. So the points of intersections are to be located for these two edges in this fashion. Okay. For this particular part, if you have any confusion, I can repeat it. So you can speak out if anyone has any confusion, I can repeat the process again. Should I assume that it is clear to everyone?
So please
Could you
repeat
repeat?
the B dash D dash part.
Okay. Yeah. So what I am saying is, when we have this section plane passing through this solid like this, and we assume this part is removed, and then we are drawing the sectional top view. So we need the corresponding points wherever the section is offering. We need to locate them. Here this O dash C dash is intersected by this at this location. So we simply draw a projector from here onto the top view of OC and we locate the point here. Same thing we do here. Here the section plane is intersecting at this location, O dash A dash. We draw the projector, go to the top view of the slant edge OA and the intersection point we locate here. This thing actually is failing for this part, right? And the reason is that OD and OB, these actually become coincident with the projector drawn from this location. From here, if we draw the projector, it becomes coincident with OB and OD, right? So we won't be able to locate the points in this fashion. Okay. So for this, say if I have to say the general method is that any such edge which actually is becoming perpendicular to the, any such edge whose top view becomes perpendicular to the XY line actually is to be made parallel to the XY line and corresponding front view is to be drawn. Okay. After obtaining that front view, this point of section is to be located by moving parallel to XY line on that edge, on that front view of the edge after it has been rotated. That is how we have to locate it in the front view. But here, since all the slant edges are same, OA, OB, OC, OD, their top view and front view are identical their top views are identical, one thing. And for front views, of course, like for O dash, A dash, O dash, C dash, they are exactly identical, same inclinations with the XY line. Okay. So now this rotating and making parallel part, we need not do. OB when rotated will only be coincident with OA and corresponding front view will be coincident with O dash A dash. So rotation part for this particular problem we need not do and the existing diagram can be made use of. So what we do is we move parallel to this and reach this part. When we are doing this, what exactly we are doing is, see this point, say if this is a section plane passing through this location. So corresponding to this point will have a line, right? And that line actually will be parallel to the horizontal plane and perpendicular to the vertical plane. This pointer, location of the pointer, if you choose a point here, this will identify a line parallel to this horizontal plane and perpendicular to vertical plane. So the distance of that line from the XY line, that actually is this much, right? So what we are doing is we are considering a different view of this OB by keeping this parallel to vertical plane. If I draw this OB parallel to XY line, right? Then the front view will give you the true length of this edge. Okay, that is available. It's with O dash A dash. That thing we achieved. Now what I'm doing is I'm moving parallel to XY line. So I'm maintaining the same distance from XY line. So this location is not altered away from XY line. and we reach this. So we locate it where this edge will be intersected. Then what we do? From here we come down to the top view, corresponding top view. Got it? Then this is to be brought back to OB. Whatever distance away from OA it is here, the same distance from here to here. Why? Because this distance away from horizontal plane is same here also, and these edges are identical otherwise. Okay, so if we intersect it here, so the corresponding position in the top view we can get by projecting it onto this. This is the corresponding position. It will remain just the same on for this rotated position also, when rather than being in this position it is in this position. So that is why after projecting it here, come down, and then the same distance is to be marked onto this. Or I should say, if I project this here, it intersects this O dash A dash, and then we obtain it on the OA. So in whatever proportion this point here located is dividing this edge OA, in the same proportion the point should actually be dividing here at OB. So we make use of that. So that is why what we are doing is we are moving parallel to this, right? From here, parallel to this, then coming down to this. In whatever proportion this point is dividing this OA, in the same proportion OB should be divided corresponding to this point. So now the same distance we have to mark onto this. So circular arc is representing that the point is located such that the same proportion it is dividing. Same is true for OD. So like this we locate these two points here. So this gives us the sectional top view. I mean, this is the top view for that part, and then there are to be section lines. Then the portion which is retained is to be made darker, right? And you have to name all the new generated corners also. Okay. Next, we can consider the true shape. So for true shape again, we have to choose a XY line parallel to this section plane and then draw the projectors. Okay, so we draw these three projectors. So you have one projector corresponding to 1 dash, one corresponding to 2 dash, 4 dash, one corresponding to 3 dash. Okay, then we have to mark these points. So on the projector from 1, the distance away from this XY line, this much, this red line, this much is to be marked over here. That is shown here, right? One by one we can see. Here you see. So this red line shows the distance of 1 from the XY line. This much. This is to be marked down to this. Here actually the same section plane is used for as an XY line, but this is not a good practice. Please choose an XY line away from this so that there is not any overlap or the diagram is not becoming clumsy. Then distance of 4 from XY and 2 from XY, these have to be marked on the same projector because 2 and 4 are coincident here. So one projector down from here, then you locate 4 and 2 onto this. Then some same has to be done for 3 by drawing the projector over. Okay, and then you draw the true shape for the section. Okay, and side view now again using a XY line over here and then projecting in this side, we can obtain the side view also. So this I guess you guys can of course do. Here also, like these points corresponding height will remain same, front view and side view. These distances you have to either measure away from this XY line and then mark away from this new XY line, or else you can of course take them and rotate them about this point and reach, or else you can draw 45-degree inclined line and then reach here. All in all, you have to mark the same distances away from this line whatever are the distances away from XY line in this direction. Okay, and like this you will achieve it. Right, and again the part which is retained is drawn darker, removed part lighter. Okay, so I'll stop the recording here, and if you have any further doubts we can discuss.